Hey everybody, welcome back to physics. Coming at you with a dress shirt and pajama pants. Here we go. Today we're going to keep talking about our circuit unit, and today we're going to start getting the tools we need to analyze more complex circuits. So we've been spending a lot of time with simple circuits where it's really just a battery and a single component in the circuit. But now we're going to start adding more and more components to our circuit and look at the different ways that we can actually set up those components and have the tools necessary to analyze the electrical properties for each one of the components in our circuit. You ready? Strap in, let's get started. So this guy off to the right, this is Gustav Kirchhoff. He was a German physicist, and he is responsible for our understanding of how circuits work. He came up with some rules for analyzing complex circuits, and there's actually a pretty good story with Kirchhoff. I don't know how true this is, I still have to verify, but there was another physicist by the name of Max Planck that wrote a letter to Kirchhoff, and he was basically explaining that he wanted to become a physicist. Now, I don't know if you know Max Planck, but Max Planck was started the whole quantum revolution and changed everything we know about physics today. And he wrote this letter to Kirchhoff when he was young. He was like, yeah, I want to become a physicist. And Kirchhoff was like, nah, don't go into physics. We're almost done with this science. And Max Planck came in and totally changed everything we know about physics and opened up a whole new realm for us to explore. But that's besides the point. So this is Kirchhoff's circuit rules. We're going to start with the rules, and then we're actually going to dive into the circuits and analyze each individual circuit. There we go. Okay, so before we get started, let's talk about the types of connections that you'll be responsible for as a Regents physics student. The two main types of connections that you'll need to know is a series connection and a parallel connection. So we said that we're adding more and more components to our circuit. And the way we can do that is a few different ways. The first type of connection is a series connection where they're connected along a single conductive path. That's a fancy way to say that each one is connected in a way that the wire goes from one component to the next component to the next component. The current has to flow through each one of these components before it heads back to our voltage source. So this would be an example of three resistors connected in series. That's our series connection. And another type of connection is what we call a parallel connection. And components connected in parallel are connected in multiple different branches of the circuit. That terminology is called branches. And the difference here is if you follow the current coming out of the voltage source, for a parallel connection it has a choice. It can go down this path, or it could go over to this path. One of the themes for analyzing circuits is you always want to follow the current and see which path the current's going through. So with our series connection, the current flows all the way around through our connections back to our battery or our voltage source. Here, the current can split, and some of it can go this way, and some of it can go that way. All right. Before we look at these particular connections, let's talk about Kirchhoff's circuit rules. And we're going to use those rules to analyze these types of circuits and understand what's going on electrically with each of these components. Okay, so the first rule that we're going to talk about of Kirchhoff is what we call the junction rule. And what Kirchhoff said was the total amount of current entering an electrical junction must equal to the total current leaving the electrical junction. And what a junction is just the spot where current can split. So if we have a wire and we have current coming in this way, some of the current can go this way and some of the current can go that way. So anytime there's a split in our wire where it goes two different directions, we have an electrical junction. Now the junction rule is, I think, intuitive because the total charge coming into this junction has to equal the total charge leaving the junction. The junction rule is really just a manifestation of the conservation of charge. So I1, the total current going in, has to be equal to the sum of the currents coming out. Whatever's coming in has to be equal to all of the current leaving the junction. All right, that's Kirchhoff's junction rule. Total current coming in has to be equal to the total current coming out. There we go. And like I said, these little spots here, all of these red spots are what we call electrical junctions. So those are the places where current can either split or come back together, where we have multiple paths. So following our current, leaving the voltage source, this is a junction here where the current can split. Here's another junction where the current can split. And these are also junctions where the current can come back together and head back to our voltage source. So any spot there's a split is an electrical junction. The total current coming in has to equal the total current going out. That's our junction rule. The next rule is Kirchhoff's loop rule. This one's a little trickier, but I think it makes sense once you really start diving in and analyzing it. What the loop rule says is the total voltage around a closed loop within a circuit is 0. So what does that mean? Well, we have our voltage source here. We have our battery that's providing voltage to our circuit. And each one of these components here has a potential drop, a voltage drop across each one of these components. So let's say we have like a 10 volt or a 9 volt source. We'll keep it nice and split. We have a 9 volt battery in our circuit. So if we follow our current, we're having a positive 9 volt source. This is providing a potential difference of 9 volts. And then as we go through, there could be a drop of 3 volts here, 3 volts here, and 3 volts here. So we have positive 9, negative 3, negative 3, negative 3. And as you can see, going around the whole circuit, the total change in voltage is 0. Another way to say that is the voltage from our source has to be equal to the voltage drop across each one of our resistors. Now I know I showed you the swiggle line for the resistor, but this is also another way that you can see resistors in a circuit, just this rectangle. And it doesn't have to be an equal split. Like I said, this was 3, 3, and 3. This could be 6, 2, and 1. It depends on the resistors that are in the circuit. And soon we'll talk about the tools we need to figure out the voltage drop across each resistor. So again, total change in voltage around a closed loop is 0. So if the battery is giving us voltage, the voltage we lose across each one of these has to be equal to the voltage that the battery gives. And this is a manifestation of conservation of energy. Kirchhoff didn't come up with any new physics here. He basically just took what we knew about physics and applied it to our electrical circuits. The loop rule is just a manifestation of conservation of energy. The energy provided by this source has to be equal to the energy lost by each one of these components. Energy cannot be created or destroyed. Okay, that's the loop rule. And now this is a simple loop, right? Because there's only one loop inside of the circuit. But you saw before that we could have parallel connections in our circuit. So if we have a parallel connection, we have a bunch of different closed loops in our circuit, right? Let's say we have a 6 volt source. It's kind of like, ignore the colors for now. If you just look at the black, these are our wires, and we have a parallel connection where the current can split here and go to our 2 ohm resistor, or it can go to our 3 ohm resistor. What the colors are showing you are the loops that are in this circuit. We actually have 3 loops inside of this parallel connection. One loop is given by the red. So the voltage that's gained by this source, so 6 volts, here's one closed loop here. So the voltage we gain has to be equal to the voltage we drop across this resistor. So there has to be 6 volts across this resistor, because here's one closed loop. We gain 6, we lose 6. If you look at the purple connection, the voltage we gain here, the 6 volts, has to be equal to the voltage we lose here. So there are 3 different loops in this circuit. Don't worry about this too much yet. We're going to be getting into really analyzing parallel circuits a little bit later. But I just want to show you that there's a bunch of different closed loops, and Kirchhoff's loop rule holds for any closed loop within the circuit. You have 3 different closed loops here. Voltage we gain is equal to the voltage we drop. All right, let's try some examples applying these rules. Okay. All right, example 1. We want to find the current between points A and B in this circuit. So in standard physics fashion, take a look at the diagram, take a look at the question, shake it off, and then come back to it. This looks complicated, but you have all the tools necessary to answer this question. We want to find the current that goes from point A to point B. So essentially we're looking for I1. Those subscripts just label the different currents that could be in our circuit. We have the total current leaving the battery, that's IA, and that's 5.5 amps, that's a lot of current. And now we enter this electrical junction. So this 5.5 amps that's leaving the battery could split, and some of it goes towards resistor 1, and that's what we call I1, current 1, and some of the current goes to resistor 2, that's I2. Now, the current in resistor 2 is given. The amount of flow that's going through resistor 2 is 2 amps. You can imagine there's an ammeter either here or here. It doesn't matter where we put it, but it will tell us the current going through this branch of the circuit. Okay, well we have 5.5 coming in. We know that we have 2 going out over here. How much current is in I1? Well, based on the junction rule, if we know that we have 5.5 going in, we have to have 5.5 in total coming out. If we have 2 here, the amount of current in R1 has to be this is ridiculous. There we go. Has to be 3.5 amps. Remember, the total current coming in has to be the total current going out. Now, you remember in all those different labs that we had you do, we said that you could put the ammeter in a few different places. If you look at this branch of the circuit, it's 2 amps of current everywhere because there's no junctions for the current to split off. So whether I put the ammeter here, or here, or here, anywhere in this branch, I'm going to see 2 amps of current because there's no place for that current to go. All right, so we have 5.5 going in. This has to be 3.5. This has to be 2. This is we're applying Kirchhoff's junction rule here. Okay. As always, shoot me a message if you have any questions. All right, let's try example 2. So we have a 9-volt battery, and it's connected in series to 2 resistors. We have R1 here, and we have R2 here. The potential drop across resistor 2 is 5 volts. What is the voltage across resistor 1? Okay. So we have our closed loop here. We have a single conductive path for the current to flow. And from Kirchhoff's loop rule, we know that the total voltage going in has to be the voltage equal to the voltage drop across each one of these resistors. It's given that it's a 9-volt source. So we have 9 volts coming in. There's a drop here of 5 volts. What's the drop here have to be? Well, 9 volts here. We have 5 volts here. The potential drop across resistor 1 has to be okay. Has to be 4 volts. Again, in a closed loop, the total change in voltage has to be 0. So if we gain 9 volts from the source, we dropped 5 volts here. There has to be a 4-volt drop across resistor 1. This is an application of Kirchhoff's loop rule. All right, I hope you're feeling okay with the rules. If not, rewind, go back through them. But we're going to be using both of those rules to really analyze the two types of circuits I need you to know how to analyze. We're going to be looking at series circuits and we're going to be looking at parallel circuits. We use both those types of circuits in our everyday circuit connections, in our lighting, and in our devices. There's always series connections and there's always parallel connections. So we want to be able to understand how those two different types of connections work electrically. So let's start with series circuits. This is a circuit where we have components connected in series. We have components where the current has to flow from one component to the next component to the next component, each following one another. So we're going to be looking at series circuits first. And our goal here is to understand the current through each one of these components, the voltage across each one of these components, and the total resistance of this circuit. Okay. Take a breath. We'll dive in. First, we're going to start with analyzing the current through each one of these circuit components. I want to know the total current in the circuit. I want to know the current through each one of these components. Now, because you know Kirchhoff's rules already, you might have some ideas of how we can analyze this circuit, but let me go nice and slow, and we will apply those rules, and we can see how we can analyze the current in this circuit. So imagine for a second that we have currents coming out of the battery, right? And then we have some current flowing here, we have some current flowing here, we have some current flowing here. But we learned with the the junction rule, that the total current going into a junction has to be equal to the total current going out of the junction. There's no junctions here in this circuit. So that means the total current leaving the battery has to be equal to the current over here, entering resistor 2. Has to be equal to the current over here, entering resistor 3. And it has to be equal to the current over here, entering back into the battery. There's no place for this current to split off. So, in a series circuit, no matter which connection I pick, or no matter where I put the ammeter, we will always see that the current everywhere in a series circuit is equal. So, our first important idea looking at these complex circuits, the total current going through a series circuit has to be the same as the current through each individual component. The current will have the same value everywhere in the circuit. If you look on your reference table on page 4, you will see this long string of equal signs. I is equal to I1, is equal to I2, is equal to I3. What this is saying is the current I leaving the battery is the current going through resistor 1, is the same as the current going resistor 2, and is the same as the current going through resistor 3. If you know the current anywhere in a series circuit, you know the current through each one of these electrical components. Okay, so that's us looking at the current through a series circuit. The amount of charge flowing every second. Everywhere in a series circuit has to be the same. There's no place for the current to split off. Okay, next. So we know that the current in a series circuit is the same no matter where we look. If I look anywhere around, the current's always the same. And like I said before, doesn't matter where I put an ammeter in a series circuit, you'll always read the same current. But what is the voltage across each one of these components? What's the potential difference across R1? What's the potential difference across R2? And what's the potential difference across R3? Well, if we apply now, going back to Kirchhoff's rules, we know that the voltage around a closed loop has to be 0. There's no change in voltage if I go totally around the closed loop. So, starting here, we gain some voltage V, right? And notice for this circuit I'm giving you, even going back to the current one, I'm giving you like a general voltage V. and a general resistance of R1, resistance of R2, resistance of R3. These all can have any value we want. This is the power of analyzing things in general, because let's say this is a 9-volt source and these are 3 ohms, 10 ohms, 15 ohms. Or this is a 15-volt source and it's 20 ohms, a million ohms, and a different amount of resistance. By analyzing and deriving these equations generally, we know for any series connection what the correct answer is going to be. Okay, so we gain some voltage V here from the source. And then there's going to be a potential drop here, and a potential drop here, and a potential drop here. I might not know right now the actual potential drops across each one of these resistors, but based on the loop rule, we know that the voltage V we gain has to be equal to the voltage we lose across these 3 resistors, the drop across each one of those resistors. So V has to be equal to the sum, the drop here, V1, the drop 2, V2, and the drop here, V3. And with that, we come to our next rule for analyzing series circuits. Maybe it'll just go to the next page. Okay. Again, looking at page 4 of the reference table, you will see this string now of plus signs. What this is saying is the voltage supplied by the battery has to be equal to the sum of the voltage drops across each one of these resistors. And notice for all these things there's a dot, dot, dot here. I'm only giving you 3 resistors for this circuit, but I can add a 4th, a 5th, a 6th, and the equation will still hold. You have to just put in plus V4, plus V5, plus V6. Okay, so the voltage I gain here, let's say it's 10. There's a voltage drop here, 3. There's a voltage drop here of 4. There has to be a voltage drop here of 3 because the total change has to be 0. Whatever we gain has to be equal to whatever we drop across each one of the resistors. All right. Now, these rules are powerful because we have Ohm's law to analyze different things with each one of these components. But now we also have these rules. Like if I know the voltage drop across 2 of them, and I know the source, I immediately know the voltage drop across the other resistor. And this is all important stuff for us to know because we want to make sure that we're always delivering the correct specifications to each part of our circuit. We don't want to burn out any of our resistors. We want to blow up any of our technology. By using Kirchhoff's rules, by using these series circuit rules, and later the parallel rules, we're always confident of the electrical properties of every single point in our circuit. All right, next. This thing's killing me. There we go. So I want to talk about this idea of equivalent resistance. I said before that we want to look at the current, the voltage, and the total resistance of the circuit. What I mean by total resistance is what's the resistance of all of these resistors put together in a series circuit. Another way to say that is if I took these 3 series connections and I took them out and I replaced them with a single resistor, what should be the value of that single resistor? Okay, the equivalent resistance. So let's define this real quick. In the reference table, equivalent resistance is denoted by capital R with a lowercase eq. The equivalent resistance is the overall resistance of a collection of resistors. And that collection could be a series collection, and later we'll be looking at a parallel collection of resistors. And by knowing the equivalent resistance of the circuit, that's useful because we can use the equivalent resistance to analyze the electrical properties of the entire circuit. Like I said before, if we replace the group of resistors with a single resistor of equivalent resistance, having that value, the circuit will have the same electrical properties. So if I put 5 ohms, 10 ohms, and 15 ohms in series, what's the total resistance, the equivalent resistance of this circuit? How do we find it? Okay. Now, you might have some ideas in your head. Well, if the current is flowing through a single path, won't putting more and more resistors in series increase the total resistance of the circuit? And that's good that you have that intuition, because that intuition is correct. But how much does it increase the resistance of the circuit? Okay. So here's how we're going to analyze this. We're actually going to derive the equation for the equivalent resistance. What kind of math can we do to these 3 resistors to figure out the total resistance of the circuit? Let's start with this rule here that we learned. The total voltage given by the source has to be equal to the voltage across each one of the resistors, the sum of the voltage across each one of those resistors. Our goal is to find the equivalent resistance, and we have a way for us to analyze resistance. We learned Ohm's law a few lessons ago. Ohm's law states that the resistance of any one of these resistors has to be equal to the voltage divided by the voltage across divided by the current through that resistor. And if I mathematically rearrange this, we can see that V is equal to IR. Okay. If I can find the total I want to find the total resistance across the circuit. So what I'm going to do is I'm going to take this equation here, how the voltage is equal to the current times the resistance. I'm going to plug that in for each one of my components. So the total resistance, the equivalent resistance, times the current, the total current, is equal to the resistance of R1 times the current through R1, the resistance of R2 times the current through R2, the resistance of R3 times the current through R3. This just follows mathematically. But we also know that the current everywhere in a series circuit has to be the same. So these I's, they go out infinitely. They all cancel out because they're the same value. I lost it. Come back. There we go. So the equivalent resistance, the total resistance of a collection of resistors in a series circuit, is simply the sum of each one of the resistors. So if I want to find the total resistance of this circuit, I know this one is 5, this one's 10, and this one's 5. The total resistance would be 20 ohms throughout the whole circuit. We just add up all the resistors. Now you might be asking, Mr. Hatzfeld, why did we go through all this just to get to a summation? Well, we had an intuition that it would increase as we added more resistors, but we have to prove why it increases based on this mathematical relationship. And now we know, because we proved this, we all agree this, and we go through each step, and we now know the equivalent resistance for a series connection is just the sum of all of the resistances in the circuit. That's the power of proving things mathematically. It makes it true not only for this series circuit, but for all series circuits that we could ever see. The equivalent resistance of a series connection is equal to the sum of each resistance. The total resistance increases with each new resistor. So all I need to do to find the total, the equivalent resistance, just add up all of them. And as we add more and more resistors to a series circuit, we're increasing the total resistance of that circuit. Okay. And now, if my computer will listen to me, there we go. Here's some examples of some resistors in series. We have these two 6 ohm resistors connected in series. This is the same as putting a single 12 ohm resistor in the circuit. We can replace these two, put a 12 ohm resistor, and the circuit will have the same electrical properties. What's the total resistance of these 3 6 ohm resistors? Well, based on our equation, we know that this is just 18 ohms. If I add 4 6 ohm resistors, it's 24 ohms. And if I added another 2 ohm resistor on the end, this would be 26 ohms. You just add up all the resistors in the series connection, you will get the equivalent resistance of that series connection. Okay, now took that long explanation to get to our 3 rules for series circuits. In any series circuit I could ever give you, the current is going to be the same everywhere in the circuit because there's no place for the current to split off. The voltage of the source is going to be equal to the voltage drop across each one of the components in the circuit. You just add up all the voltages across each component and you'll get the voltage of the source. And finally, the total resistance of a series connection is simply equal to the sum of each resistor in the series circuit. Okay. The next thing we're going to do is we're going to use these rules to analyze series circuits. I'm actually going to give you some real life series circuits with a voltage source, ammeters, and true values for the resistors, and we're going to see if we can know the electrical properties for all of the components in our circuit. Once we learn that problem-solving strategy and apply it to series circuits, we're going to use that problem-solving strategy, apply it to parallel circuits a little bit later on in the future. Okay, I hope you're all doing well, and I will see you soon. Turn me off.